Okay, now let's look at the commutative and associativity of composition of function. So when it comes to commutativity, let's say you have function f and function g, okay, and in such a manner that both are possible, like fog is also possible and golf is also possible. Let's say if this is the case, then when golf will be possible means that first you are applying f, and then the output of f you are applying g. Okay, so this is nothing but this is golf, and fog is first you are applying g, and then the output of g is going to f, and then whatever the output of f that you get. So this is fog. Okay, because if it is golf, what it means g of f of x. So first you are applying f and then you are applying g. Fog means f of g of x. So first you are applying g and then f. For golf to hold means that the domain of f should be the superset of range of f. Similarly, for fog to hold, range of C, that is D, should be a subset of A. So let's suppose both fog and golf exist. So I will take one example where F is from R to R and G is also from R to R. So I don't have to actually give an example. We can directly say that commutativity does not hold, because it might be the case that golf is possible and fog is not. So based on this, you can simply conclude that commutativity does not hold. And let us take an algebraic expression and find out fog x and golf x. Fog of x means f of g of x, which means that f of, okay, let's say something, f of x is 2x plus 3 and g of x to be let's say x square. Then f of x square, and this f of x square, this will become 2x square plus 3. And let's try to find out golf of x, then this is g of fx. Means that golf of x is equal to g of, and f of x is 2x plus 3. Okay, and g of 2x plus 3 means 2x plus 3 square, which is equal to 4x square plus 9 plus 6x. So clearly 2x square plus 3 and 4x square. So clearly fog of x is not equal to golf of x. So golf and fog are not commutative. Okay. Now let's look at associativity. Let's take f of x is from R to R, and f of x is equal to 2x plus 3. G of x is R to R. G of x is equal to x square, and h of x is also from R to R, and h of x is equal to let's take h of x to be just x. Okay, f of g of h means f of g of h of x, and this is f of g of h of x. And this is x only. So f of g of x, this is f of g of x, and this is g of x is x square, means f of x square means 2x square plus 3. This is fog of x, 2x square plus 3. Now let's try to find out this f of g of h. How do we do it? this is equal to f of g and h of x, and this is equal to fog of x. This is equal to, because h of x is x. Now this is equal to f of g of x. This is equal to f of x square, and this is equal to 2x square plus 3. So associativity holds. Okay. Okay. So associativity holds. Okay. Now, if you want to do it some other way, let's say we change the expression and see what the answer is. So let's say h of x is 2x plus 3 and f of x is x. F of g of h is equal to f of g of h of x, and h of x is 2x plus 3, f of g of 2x plus 3. Then this becomes f of g of 2x plus 3, and then g is x squared, so f of 4x squared plus 9 plus 6x, and f is simply x only, so it is equal to 4x squared plus 9x plus 6x. Okay, f of h of x, so this is equal to fog of h of x is what? H of x is 2x plus 3. So fog of 2x plus 3, this is equal to f of g of 2x plus 3, which is equal to f of 2x plus 3 whole square, that is equal to 2x plus 3 whole square, which is equal to 4x square plus 9 plus 6x. So associativity holds. There's one more thing about the composition of function that you can think of, which is when a function is in composition with its inverse. Like for example, f of f inverse of x. Okay, so it means what? It means this is equal to f of f inverse of x. So let's say if f is a function from a to b, okay, and if there is any element a which is x1, and x1 is mapped to, let's say, y1, this is set a and this is set b. Okay, f is from a to b, then f inverse is from b to a. If f of x1 is equal to y1, it means f inverse of y1 is equal to x1. So if I do f of f inverse of y1, what you get? You get y1. So we can say this is nothing but f of f inverse of y1 is equal to y1. So actually, for f of f inverse will give you an identity function. Okay. Similarly, even if you do this is going to give you x. F of f inverse x is equal to x. Okay. Similarly, if you try to find out f inverse of f of x, then this is nothing but f inverse of f of x This will also give you x only. Let's try to do f inverse of f x 1. This will give you, sorry, f of x1, this will give you x1. See how? Because f of f inverse x1 means f inverse f of x1, this is equal to f inverse f of x1 is y1 and f inverse y1 is x1. Okay, so let me write it again. Whether you go this way or you go this way, both is going to give you an identity function only. I think composition of function is over now. Okay, in the next video I'll start limits, or maybe one more video. In that video we will see some special functions. Okay, thank you very much.